Hi, I'm Aidan Chadha and my partner is Williamson. For this project, we are going to be using resistance 30 for resistor 1, 35 for resistor 2, and 55 for resistor 3, for a total resistance of 120. For our battery voltage, we are going to be using a 24-volt battery. Here we have a drawing of a simple circuit diagram. On the left of the drawing, you see a symbol of a battery with two lines, a positive and a negative symbol to symbolize the battery. The straight lines you see are the wires, and the squiggly lines you see are the resistors. Now we see in the left diagram with the three resistors as well as the battery voltage listed. As seen earlier, we have three resistors with 130, 135, and 155, and the battery is a 24-volt battery. On the right of that photo, we have our simplified equivalent circuit. This is an equivalent circuit with only one resistor. We see the 24-volt battery, a 120 ohms resistor, since this is the total resistance from all the three resistors, 30 plus 35 plus 55. Now we have the VERP table. We will go table by table to calculate the different values. In the first table, we know the battery has a 24-volt battery. As well, we know the resistance of the battery is the total resistance, so it is 120. When we divide 24 divided by 120, we get 0.2, which is the current of the battery. Since the current for all the resistors is the same as the battery, the current for all of the table is 0.2. For the resistances of all the resistors, we already know the answer. We have a 30 ohms resistor, a 35, and a 55. For the voltage of these resistors, we simply have to multiply the resistance times the current. For the first resistor, we have 6 volts, we have 7 volts for the second resistor, and 11 volts for the third. Now for the power, we multiply the voltage times the current. For the battery, we get 4.8 watts. For the first resistor, we get 1.2. The second, we have 1.4, and the last resistor, we have 2.2. Here we see a photo of the series resistor. We have the battery as well as the two light bulbs that are being lit up. Now we have a few questions regarding scenarios from the circuit. If all the resistors inside the circuit were light bulbs with the same resistance for all of them, how would the brightness of the bulbs be the same? Because all the resistances are the same, they're all drawing the same amount of power, so they will all shine the same. Now we have the question. If all the resistances of the bulbs are different from one another and match the resistances of your sample current, then which light bulb will shine the brightest in the series circuit? How can you tell? For this question, we are going to be using a CER format to answer the question. Our claim is the light bulb with the most resistance will shine the brightest. Our evidence is the most resistance a light bulb has, the more resistance the light bulb has, then the more voltage it has going through it, which makes it shine more. And lastly, for our reasoning, since it shines more because of having more resistance, then the bulb with the highest resistance will shine the brightest. Now we have a question asking what will occur if one of the bulbs in the circuit goes out. Since it's a series circuit, if one bulb goes out, then all the other bulbs will go out. Now we're going to move on to parallel circuits. On the left, we have a drawing of a parallel circuit with three resistors. As seen in the series circuit, we have a battery with the same symbol, but in this parallel circuit, we have multiple paths for the current to flow through to go to different resistors. The resistors are also shown using the same symbol. On the right, we have an equivalent simplified circuit, which is a circuit with only one resistor. Since in parallel circuits, we calculate the equivalent resistance using the formula voltage divided by current, the total equivalent resistance is 12.4 ohms, as well as the same 24-volt battery. Now we move on to the VERP table. With parallel circuits, it gets a bit different than the series circuits. First, we fill out the table with values that we already know. In parallel circuits, the voltage is the same throughout the battery and the resistors, so we put the voltage as 24 for all of them. As well, we know the resistances for resistors 1, 2, and 3, as they are 30, 35, and 55. Now we will find the currents for the batteries and the three resistors. For the formula for finding the current for the parallel circuits, we use the formula current equals voltage divided by resistance. Before we find the battery resistance, we first want to find the current for the resistors. We use voltage times resistance, and for resistor 1 we get the value 0.8, resistor 2 we get 0.69, and resistor 3 we get 0.44. Now to find the total battery current, we add up all the currents we just found and get a total current of 1.93. Now we have to find the powers for the battery as well as the resistors. For the power, we use the formula power equals current times voltage. For the battery, we get 43.62 watts. For resistor 1, we get 19.2, resistor 2 is 16.56, and resistor 3 is 10.56. Here we see a photo of a parallel circuit. We see the wire connecting the two light bulbs, as well as their own respective wires connecting to the battery. Lastly, we have a few questions regarding the parallel circuits. Firstly, if all of the resistor in your circuits were light bulbs with the same resistance, how would the brightness of the bulbs compare? All of our light bulbs would be the same brightness since they're all taking in the same amount of energy. Next up, we have the question, if the resistances of the bulbs are different from one another and match the resistance of your sample circuit, then which light bulb will shine the brightest in the series circuit, and how can you tell? We're going to use the CER method to answer this question. First, our claim. The bulb with the least resistance shines the brightest. Now, our evidence. The bulb with the least resistance has the most power, meaning it is the brightest. Now, our reasoning. Since the bulb with the least resistance has the most watts and shines the brightest, then the one with the least resistance shines the brightest. The next question asks what will happen if one of the bulbs goes out. The answer is simple. Because the current has other routes to go to, the light bulbs will stay on. Thank you for watching our video, and we hope you learned a little bit about series and parallel circuits.